We make high-performance appliances with the idea of this basically simultaneously transforming the grid. Normally, an induction stove, you have to install it on a 240-volt, maybe 40 or 60 amp circuit. In our case, we can run on a 120-volt outlet. Instead of like waiting 6 minutes or 7 minutes for a liter of water to boil, it's like 40 seconds. We're not going to stop with one appliance. So you can imagine we sell you 3 or 4 different ones. We're then in the point where we're addressing like half of your total demand.
I want to introduce you as the San Francisco's hottest DJ because of the the common misconception that you are.
We do not make DJ equipment yet.
No, okay. Well, thank you so much for joining us. It's very happy to have you. I can't promise that this is going to be Jason Carbon level banger of a video, but I think
it's big shoes to fill.
Cool. Well, why don't you introduce yourself and tell us what you're building?
Yeah. So I'm Sam D'Amico, founder and CEO of Impulse. We make high performance home appliances with the idea of this basically simultaneously transforming the grid as we deploy and sell these appliances. We're starting with the highest performing stove ever to our knowledge, and with the idea of basically just like durably proving that gas stoves are over in a performance and product sense versus in a culture war sense, if that makes any sense.
Totally. So you're building electric appliances, you're building super high performance electric appliances that basically have the ability to just pack tons of power, either heat something up really fast or control it really sensitively. I think like the coolest thing that when I was going through the materials and like learning about this, I think there are cool benchmarks of how it relates to the peak output power, or like even the normal output power of like a gas stove or a normal induction stove. Do you want to tell us about that?
Yeah, so like normally your gas stove is like 15,000 or 18,000 BTUs for like the burner on high, and maybe like your outdoor, if you use one of those outdoor propane burners, the like fried turkey or something like that. We're actually much close. Those are like 72,000 plus BTUs. We're actually in that zone, and we're in that zone in a way where it's still usable and controllable by a normal human for normal sized pots and pans, which is sort of unusual. And so what this means is instead of like waiting 6 minutes or 7 minutes for a liter of water to boil, it's like 40 seconds. And to scale this for people from like a culinary perspective, a box mac and cheese would be like 6 cups of water or about 1.5 liters of water. That takes a minute on our system. It takes like 10 on a gas stove. So it's like there is like straight up a like performance and time sort of experience aspect to this that's kind of crazy, where we can almost fully kick away the like a watch pot never boils or whatever urban legend. It gets relegated to the urban legend zone.
You're taking away our childhood sayings about
yeah. They don't matter. They don't matter anymore. Technology is accelerated.
That's right. Hell yeah. So yeah, tell us. Tell us how it's possible. Like, how is it? Because you're not having any sort of you don't need me to upgrade my panel. You don't need me to do anything fancy to my house. Basically, I just plug it in and the thing works. So how?
Yeah, so the way we do this is we put a lithium iron phosphate battery pack inside the appliance, and then that battery pack is super high power output and able to actually really push a lot of energy or a lot of power into the induction drive system. So this is also, in fact, an induction stove. And we're able to do that well in excess of what your normal wiring in your house would be able to be. So normally an induction stove, you have to install it on a 240-volt, maybe 40 or 60 amp circuit. In our case, we can run on a 120-volt outlet because of the same effect. Basically, the battery buffers and stores energy over time. And then when you need to use the ultra high power levels to boil something or things like that, it will release it in tiny bursts to get things up to temperature, basically. And so from the consumer perspective, you get a high-performance stove that works identically to any other high-performance stove, but the install requirements are dramatically less. It's a lot easier to fit within maybe, if you're in San Francisco, you may only have a 100 amp or 125 amp panel for your apartment. You're able to fit home appliances with this architecture in a system like that, whereas before you couldn't do that and you'd be stuck with gas appliances because literally your electrical system in your home is not big enough.
Can you talk about what volts and amps and watts are and things and how that relates to what somebody actually has normally in their house?
Yeah, and I think the way to do this is use water as the analogy is kind of the best way to describe this stuff. So when you hear something as volts, amps, or watts. So watts are power. So this is horsepower in your car. This is This is
the total output of the system. It's what the system can do.
Yeah, it's what the system can do. Now, volts are kind of how high on the hill you are, and then amps are kind of like how wide the stream is, if that makes any sense. If you're using this in a pure water flow analogy. And so volts times amps is kind of, you get power effectively. And so in our case, it's like what you're limited by in a typical home is when you talk about 120 volt appliances, 240 volt appliances, you're limited by two things. So one is like the thickness of the wire in your house dictates how many amps your house can draw. And so typically, like if you're in San Francisco, you might even see people getting this done or waiting for it to get done. You'll need to get your utility to physically upgrade the connection on the pole to your house to be able to support more amps into your house. Now, additionally, like a lot of major home appliances are 240 volt, not 120 volt. And so you basically get double the power on the same wires. Now, that 240 volts is actually like 220 volt connections that are actually kind of like stacked together.
Oh, I didn't know that.
In what's called split phase. So if you actually go look at the wiring coming into a typical home in towns and cities where it's overhead wired, you'll actually see 3 wires entering the house, and it's you'll see it's like hot, neutral, and hot. The 2 hots, if you get a multimeter and measure across them, you'll see 240 volts, and then from the neutral to any of the 1 hots, you'll see 120. And so that goes into your house, typically connects to what's called your electrical panel, which you've probably had to flip a breaker on once or twice. And then you see 2 sides of the breaker. The left side is one of the so-called phases, and then the right side is one of the other so-called phases. So across the 2 sides, you'll see 240, but then from the left to the center and the center to the right, you'll see you see 120. And so you end up in a situation where, based on how stuff was wired in your house before, you could only have a 120 volt cable on a 120 volt breaker going to your kitchen. So if you have a gas stove today, that's likely what you have, because that's all you need to run the igniters. If you want to put in an induction stove today, you will have to, 1, increase the voltage to get to 240. So you'll have to install a new breaker in your panel. But 2, you have to increase the amperage. You have to put thicker wires from the kitchen to your panel. And that means that you have to get an electrician to come in. And it's in San Francisco, this is more expensive, but like US nationwide, this is maybe $500 to $1,000 sort of price range to do that. The next problem, though, is you may only have a panel that's got 125 amps total capacity. And if you then run into that problem, you're now looking at like a $3,000, $5,000 ordeal where it's like you have to rip out the entire core of your home electrical system. And it can be worse because your house could be 100 years old. Your panel and all the wiring seems to be out of date, and it could actually force you to do much more expensive, much more invasive electrical work to kind of like true up to the latest standards. So sounds terrible, but then this gets worse, which is the wiring from the street to your house could be undersized. And this gets really nasty because it could literally mean that the conduit, like the pipe that the cables go through, could be too narrow to run thicker wires. So you're now into like, you need to get a general contractor to come in. Like you need an electrician, you need a general contractor, you need to make sure that you like don't like, you're putting holes in the side of your house, you have to make sure you seal those right. And you could do all that, and you could probably spend like thousands of dollars. And then you have to wait for Pacific Gas and Electric or whatever your utility is to come around to actually run the wires from your updated conduit to the street. That is like a $10,000 exercise. And it's not just a money thing. It's like I think the current lead times in the Bay Area are 18 months for literally running new wires from your house to the existing transformer. And then you just mentioned transformers. If you were one of the last people on your street to request one of these, and by the way, all your neighbors are doing this, even if they don't care about their stove, because they're getting an EV or something like that, you have to potentially pay to upgrade that transformer. And so you're then in the situation where, like, basically the deck is stacked against you all the way up the stack. It's kind of highly, I think the right way to put it in kind of the extremely online sense is this is highly cursed. So
you're not getting an induction stove. If that's the situation you're in, you're just not getting an induction stove.
Yeah, so my next door neighbor did a whole home remodeling situation and basically was considering it, didn't end up doing it because it was just too dramatic in terms of what the situation would be. There's a fix, which is, what if you could supply if you look at how all these appliances, and it's not just stoves, it's like stoves, ovens, hot water heaters, laundry machines, they're only in use for tiny fractions of the day. they're not like continuously on ultra high all the time, if that makes any sense. And even for cooking, if you're cooking like, even you're running like a Uber Eats kitchen in like at your house, like you're not leaving all the burners on high with an electric stove like you might do with a gas stove in a commercial kitchen or something like that. And so you're in a spot where there's this huge intermittency with all these things. So if you could solve the peak power supply problem without having to do any of the upgrades by virtue of putting the peak power supply in the thing that's going to cause the new peak load, you have completely solved the problem. This then basically is kind of what Impulse does. It's like you essentially embed a peaker power plant in all the next generation home appliances, which then means all the wires going to them can be skinny because none of our products have like a traditional peak load. They're all like essentially programmable lower capacity loads or lower current loads.
Yeah, that's awesome. I mean, and really secretly what that means is that you're upgrading the entire electrical system of the house without needing that massive effort by PG&E and by you upgrading, like ripping your walls out and stuff. You're just literally, like, the literal installation is you plug something into the wall.
Yeah, so there's two ways to install our products, and I can go into some of the details of that now, and I think some of this we'll cover later.
Sure.
But basically, our plan is you install this thing just like you'd install any other appliance. Like there's no special requirements. But we can change the power cable between a couple different configurations. So it's like whatever your wiring ends up being there, we support.
Today's episode is brought to you by NordVPN. Now, there are lots of reasons why you'd want to preserve your privacy and secure your online browsing. There's the normal reasons like not wanting to get hacked, which is pretty essential for deep tech companies like the ones featured on the show. But there are also some other ways that VPNs help you that are less known. Like you can get deals that are only available in certain countries, and you can get access to shows and other media that are, again, country specific. And if you're going to get a VPN, use NordVPN. They're the fastest on the market today. To get the best discount on your NordVPN plan, go to nordvpn.com/firstprinciple. So you'll add on 4 extra months to a 2-year plan. And there's no risk. There's a 30-day money-back guarantee. So check out that link, which is in the description of this episode, or go to nordvpn.com/firstprinciples. Let's get back to the show.
So do you mind telling us about like how is power transmitted, how is power used by normal appliances, and how that all relates to this AC versus DC thing?
Yeah, so we can go back hundreds of years or 100 plus years. But basically the situation is direct current is the voltage is essentially steady. So it's like how a battery works. Basically, it's like you have a alkaline battery. That thing has 1.5 volts across the terminals. It's not changing at any given time. So it's just steady. It's a steady
flow out of the battery. It doesn't matter. There's no waves or whatever. It's just getting the power.
The voltages like there's no high frequency components in the voltage. Now for AC, what you do is the voltage is modulating typically in a sine wave. And so that's and so when you see 120 volts, that's actually the root mean square voltage of the actual voltage. So like you actually can get the peak is actually higher than 120. It's like, but basically it's like that number is a root mean square voltage. It's not actually like the voltage actually swings between negative like 100 plus volts and positive 100 plus volts basically. What this does, and this is kind of goes back to the Edison versus Tesla war of the currents and all this other stuff. The advantage of AC is you can use transformers to convert AC voltages to other voltages while preserving the power transfer. And so the example would be like you have a power station, like let's call it on the Hudson River or something like that, and you want to get the energy to New York City. That station, you'll up-convert the energy, and I'm using this kind of in the Edison analogy, so New York-centric. You'll up-convert the energy to much higher voltage in the thousands, tens of thousands, hundreds of thousands, often sometimes in the millions of volts. And then you send it over the high voltage lines that look like really gigantic structures you'll see like kind of when you're driving through the countryside and stuff like that. And then when it gets to the city, you start stepping it down to the lower voltage, and then it ends up on the poles distributed to the transformers. And then that gets stepped down eventually to the 120 and 240 volt service that I talked about earlier. And the advantage of this is, and this goes back to, why do you need to do this? Like, why do you need to do this at all? And so the real reason is higher voltages you can send over longer distances with less loss. And this is because of there's the loss term for basically the power loss over so every wire is what's called a resistor. It can technically impede the flow of current. Now, you ideally want to design your wires to not be good resistors. You want them to not really resist the flow of current, but if you have hundreds of miles of wire, it will have some resistance. And so what you'll do is you'll basically, when you think of this, the square of the current times the resistance of the wire is actually the power loss you can have. So there's a real advantage to lowering the current that you send across transmission lines. And the best way to do that without having to like lower the power you're transferring is to increase the voltage, because the power transferred is V times I, but the losses are I squared times R. Mm-hmm. So if you can basically increase the voltage, you can basically have more capacity in terms of power over the same size wires. And so this was a big deal because if you can use alternating current to easily transform low voltage to high voltage and back, it makes it a lot easier to distribute electricity nationally, or globally as well. And so then I mentioned this thing called the transformer. I should explain how that works. The way a transformer works is it's basically you have let's call it a ferromagnetic core. So you can think of this as you can think of this as a big chunk of iron or something like that. And then you essentially have two coils. The coils convert the current into a magnetic field. That magnetic field, because you're running an AC, is moving. So it's basically that is now alternating. That conducts through the iron core, ferromagnetic core, to the other side where you have a different size coil. And the relative ratio and number of turns of the coil defines the voltage that is output on the other side. And this is definitely something that requires a little bit of an illustration, but essentially you can convert electricity into a magnetic field, and then you can convert it back into electricity at a different voltage while preserving the energy.
Yeah, this is like the most miraculous thing for people who have never seen it before or never done these experiments. Like the original experiment was done by this guy like Hans Christian Ørsted, or I don't actually know how to pronounce his name, but he was the first guy to realize that if you put an electrical field next to it would basically become a magnet. Like it would move a little compass needle. And then Faraday was the guy who actually started proving this, proving how this design worked, where you could have these looping coils around a metal something or other, and that if you plug in a battery to one side, then on the other side you actually still see voltage. It's like it's converting to the magnetic field and then back to electricity again. It's extremely cool, and that's the principle. That's literally what's happening in that transformer outside your building or whatever, on your block. It's coming in at a very high voltage. There's fewer loops on the side that's closer to your house or whatever, and so it's stepping down the voltage as it comes to you.
Yeah,
very cool.
Exactly. Yeah.
So now we've talked about the amount of power that's normally coming into your house is 120 volts. The amount of amps is not that high, so you don't have that many volts to distribute across everything. But you're still delivering this extremely high, voltage experience, so this high amperage experience, even without that, because of the existence of this battery. So do you want to talk a little bit more about the battery, why you chose the particular chemistry you did, how big the battery is, that kind of stuff?
Basically, when we set out to do this, there's kind of some interesting. This is actually one where there is a performance requirement, and then there's a policy and regulatory requirement, and there's a couple other things. So first thing, you put a battery in someone's house. You want to check the IRS tax code. And so, which is kind of funny, because if you're a 3 kilowatt hour battery, you are eligible for the investment tax credit as a home battery system. And so being very conscientious of that, you want to make it at least 3 kilowatt hours. So that's one. And it's actually funny is we could have probably made the battery smaller in the product because again, you only need it intermittently for boosting. You don't in some sense, this is a weird product because it's the fact that it can run itself when the power's out is a bonus. It's not actually we're not designing around that, but you get 3 uses when the power's out. So you can use your stove in pretty much all but the worst outages without actually noticing that the power's out. The second thing was basically, can you get enough, you have to size the battery enough. The batteries can't discharge in 0 time. They have to, there's a maximum discharge rate usually related versus the capacity that they're able to do. This is what's called the C rate. So it's you can, you can discharge a battery, like a 3C battery, you can discharge in 20 minutes. Or like the peak discharge rate is within 20 minutes. And so what this means is, it means you can discharge the battery 3x its rated amp hour capacity. So you can say a 3 amp hour battery you could discharge in at 9 amps. Now that's the other limitation. So then it's kind of like, okay, what's the max power we want to use the stove at? And then you size the battery for the max power that the stove would draw. That's the second design parameter. And the third design parameter is like, hey, there's a fire safety concerns on lithium ion batteries.
Hey.
You need to get this thing vetted for indoor installation, and you need to basically check all the boxes for like, people are like, you're putting a battery in a stove, like that is a fire safety thing, like just like waiting to happen.
Right.
And so now induction doesn't actually get the stove hot, like it gets the pans hot. So like you solve that problem. But the second piece about this is you want to make sure that you kind of dot your I's and cross your T's on the fire safety thing robustly. And so that, and then the fourth one is cost. And so coincidentally, points 3 and 4 point in the same direction, which is using lithium iron phosphate, not lithium, like traditional lithium manganese cobalt or like these other higher energy density technologies. And so once you have that requirement, you're now like, okay, let's figure out how to fit a battery with all those requirements into a product that's like a cooktop or something like that. We got lucky that this was barely possible and pulled it off.
Because I mean, the type of chemistry you've chosen is a little bit heavier, so it's not something that you would want to put in a car.
Higher volume. It's also higher volume a little bit as well. But yeah, heavier. It's like you don't want to put it in a car. Well, you don't want to. Actually, what's funny is that's starting to change as well. So because like it's got better safety characteristics, like it's easier to build a battery pack with lithium iron phosphate. And so if you go buy the base Tesla Model 3 today, to my understanding, that battery pack is built, I think that battery pack is built by CATL in China.
Interesting.
Basically, LFP is starting to take over in the automotive space, driven mostly by the Chinese battery pack manufacturers and the automakers. The NMC like packs, or what you see in the higher end vehicles like Tesla, I believe Hyundai also uses NMC, etc. There is actually, it's something where initially LFP was only a stationary storage thing, but it's starting to kind of crawl into the rest of the use cases as well, because its energy density itself has also improved over the last 5 years or so. And
so that was how I thought of the trade, was that, oh, it's bigger and it's heavier versus, it's safer, basically.
I should explain the safer part. It's basically, it does not have enough internal oxygen to like sustain a chemical reaction without external oxygen. So like if there is if you have a thermal event, as they say it in these parlance, like in some sense, it's like it won't like self-sustain into a like unextinguishable fire.
That's what runaway means. Like thermal runaway just means there's not enough oxygen within the thing.
No, thermal runaway means thermal runaway is when a battery pack is like essentially self-oxidizing its own fuel. And essentially it's like you can't put it out without, the only way you can really put out the fire is if you you essentially have to like rapidly cool it to like take it out of reacting with itself, basically. That's like the commonly described failure mode for lithium ion batteries. The point is, for lithium iron phosphate, it's dramatically more difficult and in some cases impossible to have the same failure modes as traditional lithium ion.
Which is great if you have it in your house.
Yeah, and then it also makes it a lot easier from like a testing and validation perspective to like pass the tests required for indoor use.
How much of that does that end up being like a pretty big driver of trying to get one of these things onto the market, is like passing all the consumer safety stuff?
Yeah, that's a huge aspect of this.
I don't know anything about it. Like, tell me, what are those tests?
This is yeah. So there's all sorts of different requirements you have to meet here. So it's weird because you think of this from a like, is this legal perspective, and it's actually, this is done by third party standards organizations like UL and CSA that set up the kind of they set the standards and tests and stuff like that. You're not legally required to do this per se to like make a product that people can buy, but all the building codes and various electrical codes and stuff like that all list these requirements in there. So it's almost like indirectly it's kind of a quasi legal regime that you have to go pass and be super diligent about. And like that's something that we've been like from day zero. It's like making sure that we design our systems with that in mind. because you're doing something ambitious and tricky, you have to make sure that it's also going to be legal in like, and when I say building codes, it's like down to towns and cities having their own individual building codes that cite these regulations. So these standards.
Got it. Yeah. So no battery fires in houses.
It's not just the no battery fires. It's like how like functional safety for like the stove to make sure that like it turns off and like things like that are also covered by this as well.
While we're talking about batteries, I wanted to ask you about sodium ion batteries. I think that you're pretty excited about them from what I understand, and I would be curious to hear why.
Yeah, so sodium ion has like also dramatically better safety characteristics. The energy density situation is, I think, at the moment worse than lithium iron phosphate, but it's not that much worse. And then there's also cost as well. So like there's no lithium, and so there's some very interesting things going on there. My expectation is there will be, I think there already are cells sampling in some volumes. I'm not sure if there's any product shipping with them yet, but they likely will be in 2025. And so there's going to be, I think, a bunch of motion in that direction very soon, and that's going to be pretty exciting. The other thing that's interesting is there's some regulations that are only specify lithium batteries. So if you use sodium, you might sidestep them. That might change though. So I'm not, that's like
don't bank on that
by half kind of thing. So not banking on that, but yeah, generally the safety characteristics are dramatically better. Plus cost is also going to be dramatically better. So it's going to be very interesting to see what's going to happen in the next couple of years.
Yeah. I mean, I think that people are talking about batteries a lot as kind of a solve to additional climate change things. Basically, like it allows us to use renewables in a way that we can't otherwise. Yep. Like, do you want to talk about that and specifically how your size of battery helps with it? Because it's not like, I mean, a 3 kilowatt battery is big enough for this purpose, but it's not huge and it's not, covering your whole daily usage of electricity. So yeah, why don't you talk about that, about how, how much electricity people are using, why it might help to have batteries in the house, how big your battery is, that kind of general thing.
Yeah, I'm probably gonna stick my foot in this, but it's like, it depends on where you live in the country. But like, imagine a typical single family homeowner in the US, they're consuming like 20 to 30 kilowatt hours a day in total energy. So that's if you have an electrified house. Like if you got AC, and ironically, this is like not San Francisco. This is like Florida. It's like where you're fully electrified. You got an electric stove. You got an electric like AC. You don't have a heat pump because it doesn't get cold. Like, but you get the idea. Yeah. And so what? You imagine using 20, 30 kilowatt hours. Now, we're not going to stop with one appliance. So you could imagine we sell you 3 or 4 different ones. We're then in the point where we're addressing like half of your total demand. Which then you think of that and you're like, okay, that's pretty notable. The other piece of this that's interesting is there's this whole nature of how people live their lives, right? Like, so people aren't consuming electricity uniformly from their house at 100% rate all day. They're consuming electricity. They're basically not consuming any electricity in the middle of the day, and they're consuming when they're at work, and they're consuming like the peak demand is from 4 to 9 p.m. or something like that, typically. And so if you can largely address those peaks with the storage, you can dramatically reshape kind of like how the grid needs to be optimized for distribution and stuff like that, because like you might have completely clobbered like the entire nature of having a quote unquote peak at that point if you've got like, let's call it 10 kilowatt hours of storage or something like that.
Because ideally you would want it to be perfectly uniform. Just from like, if you were a solar farm and you were designing how people actually use your electricity, you would want it to be, roughly throughout the day. You would though, because you don't want it to be. You don't want to. Okay, tell me then why am I wrong?
No, you want it to match your basically. So this actually goes back to a bigger issue, which is people don't understand how the electricity grid works. Every electron that is produced needs to get consumed shortly thereafter, as soon as it gets goes through the wire. So like basically speed of light sort of situation. Now, because of that, it's like a real time matching situation has to happen. Because of that, and then you realize solar farms are not like they peak in the middle of the day,
totally.
So like at solar noon, or maybe sometimes before or after, depending on like if they tilt the panels or whatever. But basically, you'll end up in a situation where solar farms are variably producing electricity. The cool thing with having batteries is batteries can be variable consumers. And so what you really want is you want the batteries to be able to match whatever production is happening at a given time. Not like I will constantly draw 10 amps all day. Like it's not that. It's actually you want to basically perfectly match production with consumption. And what's cool about this is like by having enough batteries, you turn homes from like homes essentially become flexible loads. So what a home can then do is a home can basically be like, okay, I will draw electricity when market pricing tells me it's the cheapest. Now, we don't have those price signals exposed in all markets, but in like markets like Texas, you can actually go at like there's plumbing to be able to pull stuff off like that. But that's the end game where effectively, if you have enough batteries, you can actually break that like real-time assumption of the network. It just greatly solves like all of these various things around transmission where it's like, okay, we need to size the wires for everyone coming home and turning their lights on and their AC on or their heater on at 6 p.m. and plugging their Tesla in at 8 p.m. Like it's like that sort of stuff is like nightmare planning. There's actually an example from the UK that has historically happened, which is called the TV pickup effect, which is because I think there was like a relatively small number of channels that had live sports. When major football or soccer games were on, people would go make tea on their 230 volt, 15 amp kettles that are crazy fast that they like to make fun of us for not having in America. Everyone will turn on their like 3 kilowatt kettles at the same time. And this would mean that they would actually have to live import electricity from France through the undersea power lines to make up for this. And this is like a real effect that's been documented. There's some videos on it and stuff like that. But effects like that like are really reinforcing of the real-time nature of the electrical system. And if you have batteries to make that squishy, it just dramatically helps kind of like the other solve is basically you either overbuild the infrastructure for transmission or you have batteries. And like batteries mean you can avoid having to do that.
Exactly. Yeah. Just to like underscore what you're saying, like I think people don't fully understand that the electricity right now that's powering my heater and powering my computer and powering like whatever, these lights, like all of that is effectively generated at the moment it's consumed.
Yes.
Like it's just, it is literally generated at this moment. So maybe it's coming from a solar plant. Maybe it's coming from the solar on top of my house. Maybe it's coming from a power plant wherever is PG&E is delivering it, but it's being created exactly right now.
Yes.
And so that's why it's a problem for renewables. Like you said, a solar plant will obviously only produce power when the sun is out. It's not producing power at night. And it's producing more power when the sun is directly overhead and shining straight down as opposed to, shining through a bunch of the atmosphere or something. And so we want to be able to use that. We want those renewable sources of energy, but we can only get them at certain times of day. They're variable. They're not always happening. And so from the perspective of like that piece of energy, you do want to find a home. You do want to find something you can productively do. And if you can't go directly consumed to charge a Tesla or to power a light or something, it's much better that you end up inside of a battery because then somebody can use you later. And that's kind of that is exactly what you're building.
Yeah. And you can actually see on like California ISOs, independent system operator for the grid, you can see like when they have curtailment of solar. And so basically if there's no place to put those electrons, you actually have to like shut the panels off in some cases. And so that's what's interesting is like adding batteries in some cases, it's like you can harvest these like otherwise discarded electrons effectively. You could actually store energy that is like free basically. Now in California, we don't have like pricing signals set up to make that exactly happen, but in Texas, they sure do. And you can see cases where like, oh, it's a really windy day and the wind farms are overproducing, but like it's like 4 a.m. and no one is running anything.
Yeah.
Like you get negative price signals to convince people to charge batteries and stuff like that. and so that's like this stuff is starting to kind of people are starting to be aware of this, and it's starting to kind of it's starting to become more front of mind. But I still think it's like it's non-obvious to people until you kind of poke into the space that, like what you said, it's like every electricity has to be used as soon as it's made, unless you have a battery.
It's funny. I think people probably don't know that Texas has their own grid. There are 3 grids in the United States: East, West, and Texas. I think that's hilarious. And ERCOT, I mean, I don't even know what ERCOT stands for. Energy something Committee of Texas. I don't know. But they are pretty innovative, I think, generally speaking, right? Like they're considered the ones. They have more of this real time stuff. They have like the trading between different things. Like
ironically, it's Electric Reliability Council of Texas. Electric Reliability Council of Texas, which is funny because they often get blamed when there is not a reliability event in Texas. That said, what's very interesting with this is Texas is probably the most progressive state when it comes to kind of modern energy markets. And as you just said, it's very, very interesting. This also has meant that like there's been an absolute boom in solar and battery deployments. In some sense, like eclipsing California in terms of build out rate, I think. This is also driven by the fact that California has like all of these micro checks and balances down to your local city council on getting anything approved ever. Whether it's like, it doesn't really matter what it is, whether it's low income housing to solar farms to whatever, like the NIMBYs will want to have their shake of it. And so Texas has a bit different state politics on some of these things, and so the combo of the market-driven electricity thing plus like let's call it less local control in terms of like what you can, if you own the land, like you're generally allowed to build on it, ends up meaning that like the renewable deployment in Texas is actually quite strong, despite kind of the red-blue divide between California and Texas.
But why is it I think this is true. Why is it true that California has so much higher gas stove rates? Like, why don't we have electric stoves?
Yeah, so that's a great one. And so this is actually because of where I will gaslight you on this. Where gas distribution to homes started was for gas lighting.
Huh.
So if you go to like the OG cities in the United States, that is where the gas infrastructure was first built.
Interesting. So it's just that we had gas infrastructure. It's not that we like did, and we just never upgraded, basically. Like we already had the solution. We had a stove that worked. We had street lights that worked or something. There aren't gas street lights anymore, are there?
I don't know if the San Diego gas lamp district still has gas lamps, but you get the that's what it says. Yeah. But yeah, someone will fact check us. But yeah, that's a factor where it's like, it's basically there's legacy infrastructure after they replace whale oil or whatever cursed thing they were using before. And then the second part is where all the kind of heavy industry was on the coast. So it's like, of course you'd have you'd have the oil and gas refineries and stuff like that, like around there. So the distribution would be easy to do because you'd have a big tank of it anyways. And so it's kind of like if you were a major urban area in 1900, decent odds you have gas, if that makes any sense. But then if you're ex-urban sprawl in Texas, 0% chance you have gas. And so, and then there's some other fun ones around building codes and other things. So like Florida, my understanding is like some of these Miami high rises can't have gas because of like hurricane risk, and if you have a gas leak, it can cause a fire. So there's also that aspect of it as well.
All right. Well, we've gotten this far and we still haven't talked about how induction actually works. I think let's do that. I mean, we hinted at it with the whole electricity and magnetism thing, but so like what's actually happening inside the stove that heats up the pan?
Yeah. So we can walk through a couple different types of stoves to kind of like clear this up, and then we'll get to induction stoves. So gas stove is really simple. It's a flame under your pot. The flame heats the air, which heats your pot. And yeah, what's interesting about that and what's not expected is it's only about 40% efficient because it's more efficient at heating the air in your kitchen than it is at heating the pot.
Yeah.
Which is a little counterintuitive. So this is also where it's like, it makes it really challenging to compare performance between various stove types because the like BTUs of the burner, then you have to map through some various efficiency scaling things to compare to say an electric or induction stove. So then let's talk about electric stove. There's kind of a couple different types of electric stoves. Induction is inclusive in that, but we'll separate that one out. The first type is like the ones with the coils that look like a spiral that are on your counter.
The red glowy spirals underneath the glass.
Or no, that one's the one that's above the glass. And in some cases, that's just like it conducts. You basically get a thing that gets hot, and the pan touches it, and it gets hot. Now, the improved version of that is what you just described, which is that's called a radiant electric stove. And the way that works is basically you have a light bulb underneath the glass that glows mostly in infrared, and it heats the pot up. It also conductively heats through the glass as well, so you kind of get two modes of heating there. The big problem with that is it takes like literally seconds for that glow to modulate. So if you like are about to burn something, you can't just turn it down because it'll still be heating your pan up even after you turn it down. So you end up having to like lift the pan off the stove and stuff like that. It almost changes how you cook. And meanwhile, like gas is like you directly adjust the dial, it directly adjusts the flame in real time. So that's like one of the things that people really like about gas stoves. Induction gives you that back mostly. And so the way induction works is the stove doesn't get hot anymore. There is a coil in the stove, but it's actually a 25,000 hertz alternating current signal. And the reason you have to go really high is for a reason I'll just describe later. So basically you're putting 25,000 times a second, you're basically sending a sine wave at very high current into this coil. That coil then forms a magnetic field that's switching at that frequency. The pan is a piece of metal, and you can think of this as actually a transformer, and it's like the world's crappiest transformer. The pan is, in some sense, you've got a bunch of what's called windings on the coil underneath the glass. The pan is one winding. It's just a circle. And so, but it's also shorted. It's a short circuit. And so what'll end up happening is you get losses in the pan, and you make the pan out of material usually has to have some steel in it. And so it's kind of high resistance. It will lose energy in that section of the circuit. And that energy loss turns into heat, which heats the pan. So the pan heats itself by virtue of being in a short circuit with the induction coil that's beneath the glass. Now, there's a couple ways this heat also happens. So basically, you also get heat through, my understanding, through magnetostriction. So basically, you're also flipping the magnetic domains inside the steel from like north-south. Like basically, you're flipping them between states at a high rate, and that also causes heating as well. But yeah, and so for this reason, you typically need a ferromagnetic, or so it has iron pan to make induction work well. There's one product I think that works with aluminum and copper, but I found out that they cheated because they just make the underneath of the glass hot. But yeah, so that's the one constraint that you end up having to have. Now, the good news is most pan makers are realizing that induction is becoming popular, and they're making sure that all their pans are compatible. So you don't really have to worry about this anymore.
Dumb question. What does it mean that the pan is a short?
Yeah, so the pan is basically a short, like you can think of this as like you have like a spiral wound coil. So it's a bunch of windings in a transformer. The pan is just a single winding. So instead you're putting a huge amount of current through that pan at very high frequency. And at high frequencies, you get what's called the skin effect, where only like the top layer or in this case, the bottom layer of the pan will actually carry the current. So you have like a very skinny wire. You can think of this as a very skinny wire that you're putting a lot of current through, which means it gets hot.
And is that, could you choose a different frequency and it would still work?
Yeah, there's a couple different things that you have to do here. So like there's this kind of goes into the weeds on power electronics design and various other things like that. There's the frequency that typically you want to do is the lowest frequency that you can't hear.
That makes sense. Yeah, you don't want it to be like screaming at you.
So, so you know that like annoying mosquito noise that like people used to like prank people with like 10 years ago that we probably both of us can't hear anymore. So that annoying mosquito noise is like just below what induction typically drives at.
Interesting. So you would ideally assume that everyone on Earth was deaf. Like, would you choose?
You could run it at low. You could run it at lower frequency. You could run it at slightly lower frequencies. Now there's kind of a sweet spot in terms of like thickness of the pan, the material, like various other things. But and then the other thing is you end up needing smaller capacitors the higher the frequency you are. So there's kind of this like, because what you're doing is the way induction drive circuits work, you're trading energy between a capacitor and an inductor in kind of a resonant circuit. So you're moving stuff between an electric field and a magnetic field back and forth. Now, the faster you do that, the smaller those components need to be. Because
that makes sense.
Because you're transferring less energy per step if you run at higher frequency.
And that's the same. That's sort of the same thing that's happening with like, wow, I'm like really getting over my skis here, but like gallium nitride,
yes,
and the GaNs or whatever. That's the same.
That's
concept,
why your
right?
power brick is getting smaller, because the magnetic components and the capacitors in there can get smaller. Exactly.
Interesting. Can you explain that just like for people who have never heard of gallium nitride before?
Yeah. So the reason your power brick on your phone has gotten smaller but like higher power over the last 10 years or so is because of advances in new types of semiconductor technology. Primarily in this case would be gallium nitride. In like the electric vehicle case, it's been silicon carbide. But we'll go to talk about gallium nitride. The primary advantage is you can switch at much higher frequencies without huge losses. And so what this means is you can essentially have a really, really, really efficient power brick that is really small. Now, the change you make to make that small is you run to convert a DC voltage to another DC voltage, which is how a power brick works. It converts AC to DC and then DC to DC. You actually convert it to, you actually have to do what's called like a switch mode power supply. And you essentially have to convert the you essentially have to make an AC waveform again inside that. That's a little oversimplification, but that's essentially what happens. And then if you run that at higher frequency, you can make the inductor and the capacitor smaller. And so that's the primary advantage. That's been the driving force for why this has been possible, is basically new transistor architectures driven by the new semiconductor technologies, enabling smaller magnetic components in power bricks.
Are you guys using that for your stove?
No, we don't. Yeah, so actually we're very conscientious on how to make sure we cost optimize the system.
Because they're awesome, but they're really expensive.
It's expensive. It's also like you don't necessarily need them. So like at this frequency we're talking about here, you do not need you do not need gallium nitride for that to work.
When the stove is heating up or cooling down, is that just flowing more amps through it? Is that basically how you do that change?
Yeah, so if you want to cool it down, you turn it off. So it works just the same as turning off a gas flame. And then to input more power, you increase the AC current in the coil, and then that proportionally means more power in the pan.
Yeah, because one of the things that I know that you guys have as a big selling point basically is like very sensitive temperature control.
Yeah.
Is that because you can change the current really precisely, or is it the more, because you also have like a temperature sensor thing that you had to figure out, right?
Yeah. So there's a couple things going on here. So one is a bunch of more usually cheaper induction stoves, and I think even some of the nicer ones, they when you go to lower power levels, they start clicking on and off. And so like simmer, and this actually works kind of like your gas stove in simmer mode, where like the burner will like click on, click off, click on, click off, versus like you could actually throttle it down really low. And so we had to make sure that we could throttle down low enough to make, micro adjustments and stuff like that. That was like one thing. But then the second piece was, the temperature sensor. If you go and increase the power of an induction stove to like 10,000 watts, which is what we're doing, you can quickly outstrip now for boiling water, it's usually fine, but you don't know if like the person put water in the pan, like if that makes any sense.
Yeah.
Like, you can't guarantee, we can't guarantee certain things like that. And so you very quickly could go into a spot where like the pan is not at a safe temperature very quickly.
Sure. Yeah.
And like for typical cooking, you don't really need to go very high. Like 500 degrees is kind of like, for a stove, it's enough. Because you're going to be, that's at the point where you're smoking all your oils, making a huge mess, like that sort of thing. But you need to basically be able to tell like, hey, is the temperature within nominal range, in real time, and ideally really fast, because like you could be in a situation where like you put a pot of water on the stove, the last droplet of water boils off, it's running at max power, and then it doesn't, like, you don't get in trouble. And so we had to basically go in and invent a new type of temperature sensor for the system that had like just way better performance characteristics than anything else in the market to make that work. The implications are actually pretty sweet though on the low end. So you can do things like sous vide a steak without a water bath and things like that. And I've shown some videos of that as well.
That's so cool. I remember, I think you tweeted about that or something, and it just broke someone's brain. They're like, what are you talking about? What do you mean that you can sous vide without the
Then
water
they roasted me. Then some other people roasted me for not searing the steak properly. We fixed that problem. Well, one thing that's fun is actually we can sear a steak without it smoking up your kitchen.
Really? Just because it's the precise correct temperature?
Yeah, you just set the temperature to be above the point where the steak goes like, you get some charring on the steak, but below the point when the oil smokes, and you're like...
That's brilliant.
And it works, yeah.
And you're doing all these cool experiments. You're doing like, you told me about this fried egg thing that you did, and you're like becoming, the next top chef. And
no, I mean, I think I get roasted, pun intended, by all sorts of folks, and like we're very excited to like get real chefs in the mix and kind of see what they can do with this thing, because I think there's gonna be some really exciting stuff that people are gonna be able to do. Not
totally.
me. The egg thing was fun because it's just like I can fry an egg in front of you, and it's like it comes out perfect every time, and I don't make eggs for breakfast because, I sleep in.
Yeah, totally. Would you ever build in like routines, like press a button, like the popcorn button on your microwave, but instead it's the fry an egg button on your stove?
Yeah, so there's actually some interesting like restrictions on what you can do in terms of like unsupervised control for stoves. For ovens, you can do some stuff like that, but for stoves, what we found is, so the answer is yes, we can do things like this. It's just there may be additional, like you have to click a button to like progress to the next step kind of thing. Like, yeah.
Huh. The man doesn't trust us around flames or like whatever.
This one is counterintuitive, but you're not allowed to have an auto off feature, because then the point is they don't want people to expect that the stove will be safe when they walk away from it.
But then what if it just is safe if you walk away from it?
Well, no, that's the thing. Like, ironically, it is safe if you walk away from it, but it's not going to turn on. Like, we're not allowed to turn off, but you can turn to like, you're not allowed to like fully turn off. But yeah, it was cool. It's like I could fry an egg in front of you, and then the pan could still be at 330 degrees or something, just like chilling, and it'll be hot, but it's not going to be like, you're not going to accidentally burn all the butter in there or whatever.
Well, what I'm really hearing from you is that I need to figure out how to jailbreak my stove as soon as I get one of these things, so that I can set up my illicit methods for frying eggs on demand.
You will struggle there. I trust our team.
Dang. I love it. Okay, well, let's shift gears a little bit and talk about sort of manufacturing. Like, how do you actually make a consumer device and get it out to hundreds of thousands or tens of thousands of homes? I know that you've obviously thought a lot about this, and like how far are you guys? Like, are you guys you're shipping sort of at the end of this year, I think, for the first batch of stoves?
Yeah, we're shipping in Q4. And that's at what I would call reasonable volumes. And that's like if you're not a friend of the company. This is like general availability. I think we're working through the production process to get through all that stuff. I don't have like detailed play-by-play I can really share, but right. I can also describe generally like what the process looks like, and like how, not exactly on our schedule, but like what the process looks like, and like, what you have to do.
I'm curious in general. Like I'm curious generally about how do you go find the right manufacturer? How do you persuade them to take your business? Because I presume that you have to, like all that kind of stuff.
Yeah. So let's start from the very first part of this, which is, okay, build versus buy effectively. And so like I'll kind of knock your probable subscriber base, because this is actually a good point. It's like SpaceX made a lot of waves by being like, we're vertically integrating everything. We're going to do it. We're going to insource as much as possible. A big story with this is, well, the legacy aerospace supply chain wasn't able to kind of keep up with what SpaceX was doing. So they had to kind of like, and also we're like going to overcharge them like massively. Like there's the quotes from the Elon book on like the so-called idiot index and things like that. Yeah. So it's like, okay, if you want to build something fast, cheap, and like reliable, it's like, well, consumer electronics is a very different beast than aerospace, in some sense. And so a big portion of this is, if you can leverage the consumer electronics supply chain, you can actually potentially even lap the legacy appliance vendors, because it's just like they've had to be dramatically more advanced and mature than pretty much any other industry at being able to do stuff like this. And so we were kind of dead set on like, let's go into the, let's work with someone in the consumer electronics space. Now, the next point is like, who's going to work with you here? And it's like, I think there's 3 different things that startups do when they go find a manufacturer. One is it's kind of like, I will optimize on some sort of local option or things like that. Then you'll eventually maybe outgrow or like, yeah, but you'll essentially be in this local maxima that won't scale you. A big story in the United States is that the manufacturers, there's a couple big major manufacturers that are quite good. They don't really work with startups.
Okay.
And so, and then additionally, the engineers that would be like, you'd want to like augment your team. You'd get people who are good at like manufacturing engineering, but they won't be able to provide like design engineers who could design a smartphone or something like that to your cost. Now, in Asia, you get like a vertically integrated team that's almost like a product team that can go and just do stuff for you. Now, getting them over the hump where you're able to do that is not trivial. Like this is not and I think I've seen 2 ways this can work. One is basically like you're a known quantity and like they know who you're, and like someone famous made some calls. And then the second one is kind of like it's something. The second one, maybe there's 3 actually. There's kind of like the known quantity one. There's the like you can convince them that you're probably a known quantity. And then the third one is like you can actually go to like more mom and pop scale places that maybe that have good equipment and access and things like that, but maybe aren't like name brands and stuff like that. And that one actually is more of the like you move to Shenzhen and figure it out yourself kind of thing, which I've heard people do successfully. I would say we're probably in that middle one, not in the first one or the second one. But yeah, so that's, you basically have to find someone who has the capability of doing this and wants to work with you, and ideally like has an engineering team that can augment your team because you're a tiny startup and like you're building something complicated. So there's that. And then the second piece is like the way of working and like how to get things across. And it's kind of like the big story is if you do stuff with your manufacturer, including prototyping, then all of your manufacturing will then translate to production immediately. Or all of your prototyping translates to production immediately. And so then it's kind of like, part of this is like when you're a new company, you have to kind of get on the horse, and that's kind of a fun exercise. But once you're established, then it means that subsequent products, it's like, oh, cool, we can just take these building blocks we already built and like things can just be really
totally
fast. There's that. There's a lot of like, I had to do a lot of kind of like dog and pony show and like a lot of FaceTime and building trust and stuff like that. I think that was a big aspect of it.
Does it look similar to how you build, like how you raise money from investors, where you're like, here's my pitch on here what I'm going to do, or is it different?
You do have to kind of do some stuff like that. It's not exactly the same, but it's like there is a little bit of a similar skill set, but it's definitely mixed with like. And then I think the bigger thing was learning how to scale down from like, I was at Facebook, Meta before, I guess most of the Oculus team back when it was branded that way, and so on the Oculus team, like it was kind of a 0 to 1 thing for manufacturing boot up, and I got to see a good chunk of it. You can rerun some of that playbook, but obviously you're not $1 trillion company, so it's like a little bit different. It's a little bit of a different situation. And
so you go out there, you pitch folks, you find somebody to bring on. How do you actually, like, you said you're prototyping with them, so are you sending them designs and then they're manufacturing something and they're shipping it to you to check it out, or like how is that actually
you send the team, yeah. So it's so it's I think that there's you basically have to be like super willing to fly out, that's the key thing. But yeah, it's actually at the level. There's a couple different ways to slice the thing. It's like you could own the whole design team yourself. Be like, here's the final designs, just go build these. That works. And then, but the thing is, oftentimes they'll want to source components. Like, you're not going to go say like, buy this resistor, or this capacitor, this inductor, this IC from this specific. Like, you don't really want to handhold them on that. It's like they will go and take care of that for you. That's like abstraction layer 1. That's kind of what that's closer to what like Meta would do for some of their programs. There's also kind of like a layer above where it's like you're using the manufacturer team to do stuff like PCB layout, so maybe some of the detailed CAD design, like after you kind of like give them the the
Cool.
industrial design surfaces, like stuff like that. And then there's much more of like this team is basically just like additional engineers underneath your team structure. And so if you can get to that point, it's like you get a lot of leverage and like it's really, really effective. But that's something that it depends on where you are as a company, what makes sense for your business.
Wow, interesting. I mean, I just know nothing about this world, so like I had so many questions. But I think my main one is like, I assume that in the early days, they're going to charge you more, like because they're providing more services to you. Is that not the case?
No, it costs more when you get closer to production because you're buying the tooling for production base. You're buying the tool. You're basically buying the factory line equipment. Is like what's going on later on. Now, earlier on, it's like, yeah, you may have like 15 engineers like doing initial design work or something like that. But like that's not, again, there's a labor arbitrage. You can like
compared to
it gets you a lot of leverage. It gets you a lot of leverage. Now, part of there's a lot of interesting effects here, which is like, when do you start the vendor engagement? And I would say like good examples are like, oh, we're figuring out the new type of temperature sensor, or we're figuring out like how best to do the induction drive architecture topology, like, or we're figuring out like the actual product architecture. It's probably not worth engaging until you've got some of the key stuff figured out. But like once you're kind of like, okay, I have a 90% plus confidence of this being the right direction, let's just shoot in a straight line now, you'll be really good. The other thing you'll find out is like component sourcing, like they will solve things through their supply chain, whereas you will solve things in like, you'll order stuff from McMaster, and like that doesn't, it's like it doesn't.
Yeah.
And so it's like, okay, then you have to translate your McMaster order into something that you can actually go build with the factory. And so that translation, and basically if you can get like most of the like later stage stuff that's kind of after the architecture's been figured out through the manufacturer, you can skip that translation step, which is a huge deal.
I'm curious to hear about sort of high level, what are the things that make you excited about this company? I mean, are there big trends toward electrification? Are there, I mean, maybe the IRA is maybe something that's in this category, like tax credits for people for this kind of thing. I'm curious to hear like what makes you optimistic about the future of this kind of thing?
Yeah. So, I think basically I'll distill this down really succinctly. It's like, we're basically building the highest performance appliances, and like the architecture for essentially power delivery, both to the grid and within the appliance, basically making that all next level. And that in a sense is the backdoor. Like basically you have this high desirability, like massive step up in performance, and you use that to bulk deploy batteries on the grid at scale. And so like the big picture here is like, I think Tesla said they only sold 600,000 Powerwalls worldwide. And so if you think of that versus like, I think that kind of implies a number that's like, and it's like the most famous home battery product. And it's like, that's like, I think it's in the order of like 1/10 the US battery capacity per year at Powerwall. They're not even like, it's a tiny fraction. A huge chunk of this is probably grid scale stuff. And so when you think of it that way, you're like, no one's really cracked the home battery thing, because home batteries have been, in a sense, like this like prepper backup thing, or sold to solar. Like it's not been this like, there's not like another reason to buy a battery. Yeah. And so what we realized is like, there's 140 plus million homes in America. You could probably get them 3 or 4 appliances with this tech. That is a 1.4 terawatt hour market for home batteries, just by virtue of saying your appliances will become more awesome.
It's a good sales pitch.
I feel like I think that's kind of like, it's counterintuitive, but it's kind of just huge. And then if you control that many batteries, you kind of are like you're the market maker on the grid. Like this is not a small situation. And so
no, I mean, that's like a third of total capacity or something for the entire, And can you flow energy the other way? Like,
yes.
Can you, are there places where that's true and not true, or is it just you can do it?
Yeah, there's local regulatory aspects of this as well. We're designing the system so it looks to your house like it's a home battery system. Some of this depends on, there's a bunch of local regulatory fun with all this stuff, but we've been working with the relevant standards bodies to make sure this actually is in fact the case.
So are you a D cell or an accelerationist? Which tell me.
Gas is D cell anyway. So the situation with this is I think it's very, you see this culture war push on like the government better not take away my gas stoves, etc. It's like I actually think the right way to approach this is like a very measured, like almost like technocratic way, where it's like my goal is to reliably kick the ass of every other stove available, and I'm not going to go like force anyone at gunpoint to go buy my thing. I mean, like I like gas stoves; they're fine. Like it's not a problem here. That said, like I think there is going to be a bit of like a indoor air quality concern situation that definitely seems to be sticking. And then I also think that new technologies like what we're doing, especially on the control side, will make it very obvious that the next generation of tech is here, and like that's gonna be the thing that convinces people to switch to electric or induction, not like, hey, I will punitively say that like when you renovate your kitchen, you're not allowed to do this, not allowed to put a gas stove back in.
Totally.
And so I think that's the way that I see it. And then also like the government, I'm generally pro the incentives they've been putting in place. I think doing this with incentives versus doing it with bans is probably the right move.
I think that about wraps it up. Sam, thank you so much for doing this. Is there anywhere you want to send people? Do you want to tell them to apply to your site or buy a stove or anything like that?
Yeah, so we're taking pre-orders now at impulselabs.com. You can also check us out on YouTube. There's a bunch of content from some of the friends of the pod and otherwise as well that you can check out. But yeah, impulselabs.com. And thank you so much.